Hi, we are Stefan, Bezel, and Elisa. We will tell you something about the 3 different topics today, connected by a single equation. How could life on other planets exist, and how big is the chance that it does? The crucible in which the necessary materials for life are created happen in a supernova. This is something that outshines an entire galaxy, and so powerful that if one were to explode within 100 light years of Earth, it would cause noticeable changes to the biosphere. It is even so powerful that if a nova is within a light year, the Earth will be vaporized. But our sun is not massive enough to become a supernova, so if you are planning on living another 4.5 billion years, you'll notice that the sun is swelling into a super red giant instead of exploding. Although destructive, a supernova is like a superhero, because it is responsible for life here on Earth. By creating elements due to nuclear fusion, this process involves the smashing of protons together to form helium and other heavier elements. Atoms become crushed so closely together that the repulsive forces of their nuclei create a recoil of the squeezed core. This results in a bounce that causes the star to explode as a supernova and give birth to an enormous superheated shockwave. When supernovas explode, they shoot out billions of atoms in every direction, resulting in the creation of colorful nebulas and heavier elements. The star spews its element-rich guts across the cosmos in all directions. Some of these guts are the fundamental building blocks for organic compounds and molecules like water. In the universe, there is a special place called Earth, where some of the supernova's guts have come together to form life. There is roughly 1.26 million trillion liters or 1/6 trillion liters of water on Earth. This water is mostly salt water, and 70% of the Earth is covered by it. Pure water doesn't have any taste or smell because it's pH neutral, which is one of the factors that makes life possible, because it would react with your body if it wasn't. Technically, it's an acid and a base, which is even more spectacular than just neutral. Water has some really cool characteristics which are crucial for life here on Earth. Water, or H2O, is made up of 2 elements, hydrogen and oxygen. Both hydrogen atoms share 2 electrons with the oxygen, which makes all the atoms happy because then they act like noble gases with an outer shell filled with electrons. But oxygen is much bigger and stronger and therefore pulls much harder on the electrons, which makes the oxygen atom slightly negative and thus the hydrogen positive. This is called polarization, which is just one of the things that makes water awesome. Because of this, all H2O molecules stick together. That's why water is liquid at room temperature. If you compare water with other molecules of the same weight, its boiling point is relatively high. This property allows water to exist in a liquid form here on Earth. We will now talk about a special man named Frank Drake, who was an American astrophysicist. Astrophysics is the branch of astronomy concerned with the physical and chemical properties in our universe. Drake is known for the Drake equation. This is an equation to estimate the amount of civilizations active in the Milky Way. The equation consists of a number of factors, as you can see here, and although almost all of these are based on thought experiments and do not give any concrete proof about life on other planets, it is a good equation to estimate the chances of how many civilizations are active today. The first factor in the formula is the average rate of star formation in our galaxy. Star formation is the process of an area in our universe getting denser and denser due to gravitational force, and when it is too dense, the particles collapse and form a star. The original estimate back in 1961 was that this number was 1 star per year, which even then was considered conservative. The most recent numbers NASA released were that the rate of star formation is around 7 stars a year in our galaxy. The second factor is that the fraction of those stars that have planets. This was estimated around 1/5 of all stars. We'll take the average to work with. Next is the average number of planets that can potentially support life per star that has planets. This can be based on all sorts of different factors. Our estimated number is 3, so that in every star that forms planets, around 3 are capable of maybe supporting life. The next term simply estimates how many of the Earth-like planets, which are capable of life, actually do develop it. This, of course, is difficult to estimate, but let's take a number estimated by Drake himself. 1. That's weird, right? 100% of these planets develop life? But on the other hand, if they potentially can and have enough time, why would life not develop on these planets? So what about the planets that can create intelligent life? Based on our former answer, the question which of these life-sustaining planets will host an intelligent civilization can only be answered the same. 100%. With enough time and the right circumstances, 100% of these planets will develop intelligent life. This one is a bit more tricky. because we are supposed to estimate that the amount of these civilizations that create a system that is detectable, like for example radio waves. Of course, there are many more ways that can be invented to communicate, and even if they are detectable, how will we know when we stumble across a sign instead of just another wave? So we estimate around 15% of these civilizations will leave trace of some detectable form of communication. Of course, there are many ways civilizations could stop sending out signals. Not because of extinction, but because they use a different method for communicating. If we fill in all those factors, we get a number. In our case, this number is 110,250 civilizations. So that's a pretty high number. To see if life exists in extrasolar systems, we have to trace back where life's simplest molecules came from. Supernovae are the origins of all of Earth's organic material. Knowing this, we can assume other solar systems are created with similar molecules, like water. Life rises under the hardest conditions, but is also easily destroyed, in a never-ending cycle, beginning with stardust and ending in stardust.